Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss RODRIGUE'S formula for Legendre polynomials. Let's begin. Why it's necessary for that of Legendre polynomials, as the general solution of that of Legendre differential equation, we have Pn of x, that is the Legendre polynomial, and it is written either in the ascending power series of x or descending power series of x, but it's not the convenient way to find out the Legendre polynomials very easily. That's why we prefer a short formula to derive that of Legendre polynomials that can be proposed by RODRIGUE'S regarding to derive the Legendre polynomials. That's the mathematical formula of that of Legendre polynomial, that is Pn of x is equal to 1 by 2 to the power n factorial dn by dxn of x square minus 1 to the power n, that is the nth order derivative of that of term. This is the formula. Now we should prove that particular formula. How to prove? Let y is equal to x square minus 1 to the power n. Therefore, dy by dx is equal to n x square minus 1 to the power n minus 1 into 2x, the first order derivative of that of y, that is equation 1. Let I prefer that as equation number 2. Now multiplying x square minus 1 on both sides of above equation, we have, that is x square minus 1 whole into dy by dx is equal to 2nx x square minus 1 to the power n. Using equation 1, that can be written as x square minus 1 dy by dx is equal to 2nx y, that is equation number 3. Here we using equation number 1. Now our aim is to differentiate that equation n plus 1 times. How this type of differentiation is done? We have to use the Legendre's theorem for that of successive differentiation. The formula for that of Legendre's theorem, as we know from Legendre's theorem, if u and v, two functions, are multiplied, then its nth order differentiation, that is dn of uv, is equal to, according to that of Leibniz's theorem, that is nc0. Let I prefer u as first function, that is nth order differentiation of u, then 0th order differentiation of v, that is v. That means nc0, that is n minus 0, that is n, that is nth order differentiation of that function u, and here that term, that is the 0th order differentiation of v. Like that of series will be continued, that is nc1. Next, that is n minus 1th dn minus 1th u, and first order differentiation of v, that is dv, plus nc2, then that is dn minus 2th differentiation of u, and second order differentiation of v, that is d2v. Similarly, we have the rth term, that is ncr, will be d n minus r differentiation of u and rth differentiation of v, plus dot dot dot. For that of last term, that is nth term, will be ncn, that is n minus 1, n minus n, that is 0, that is the 0th order differentiation of u, that is only u, and the nth order differentiation of v, dnv. In this way, we can differentiate the multiplication of two terms for that of nth time differentiation. Here I can use that Leibniz's theorem to differentiate that equation number 3 n plus 1 times. That's why I write differentiating this equation 3 n plus 1 times by Leibniz's theorem we have in that of term, let I prefer dy by dx as u and x square minus 1 as v. This is the first function, that is the second function, and in that of case I prefer x as v and y as u. Now we differentiate that equation number 3 n plus 1 times. What happened? That will be x square minus 1. Here that is dy by dx, that is the first order differentiation, when it will be n plus 1 times. That means that is the n plus 2th derivative of y, that is d n plus 2 y d x n plus 2, okay, plus, since here nc0 is equal to 1, I don't write that one. Here the coefficient will be n plus 1 c1, again d n plus 1 y dx n plus 1, derivative of that term, that is 2x, plus n plus 1 c2 d n y dxn 2 plus is equal to, here 2n as constant, 2n xy n plus 1 time differentiation, that is x d n plus 1 y d x n plus 1 plus n plus 1 c1 d n y d xn into dx by dx, that is 1. Or that is x square minus 1 d n plus 2 y dx n plus 2 plus n plus 1 c1, that is, and 2 multiplied here, that is 2 n plus 1 x d n plus 1 y d x n plus 1, that is the value of n plus 1 c1, that is n plus 1. We use the combination rule here, plus again n plus 1 c2, that value will be n whole into n plus 1 divided by 2, here 2 cancel out, that is only have n whole into n plus 1 dny dxn, okay, that value will be n whole into n plus 1 divided by 2, here 2 is 2 to cancel out, that is n whole into n plus 1 is equal to 2nx d n plus 1 y dx n plus 1 plus 2n whole into n plus 1, and the value of n plus 1 c1 dny dxn, or that is x square minus 1 d n plus 2 y d x n plus 2 plus, this is d n plus 1 y d x n plus 1, in that of side, that is also d n plus 1 y d x n plus 1, when that term to that of this side, that will be 2x here common, that is 2x n plus 1 minus n d n plus 1 y d x n plus 1, again that is dny dxn dny dxn, when that term to this side, that is n whole into n plus 1 minus 2n whole into n plus 1, therefore that term will be minus n whole into n plus 1, that is minus n whole into n plus 1 dny dxn is equal to 0. Now simplifying that one, that is x square minus 1 d n plus 2 y d x n plus 2 plus, that is 2xn 2nx, sorry n cancel out, that is only 2x 2x dn plus 1 y dxn plus 1 minus n whole into n plus 1 dny dxn is equal to 0. Now I can multiply negative sign on both sides. Therefore we have 1 minus x square d n plus 2y d x to the power n plus 2 minus 2x d n plus 1y d x n plus 1 plus n whole into n plus 1 dny dxn is equal to 0. That is equation number 4. I multiply negative sign here to get the standard form of Legendre differential equation. Now substituting dny dxn, let phi of x in equation number 4. In equation number 4 we get that will be 1 minus x square d square phi by dx square minus 2x d phi by dx plus n whole into n plus 1 phi is equal to 0. That equation number 5. This is the Legendre equation. This is the Legendre equation with which has the solution phi is equal to dny dxn as we substitute. Hence we may relate this solution phi of x, with Legendre polynomial Pn of x as Pn of x is equal to C phi of x, where C is the constant, where C is a constant. That is Pn of x is equal to C phi of x. That equation number 6. Therefore, as y is equal to, first we substitute y is equal to x square minus 1 to the power n as y is equal to x square minus 1 to the power n. That means that is x plus 1 whole into x minus 1 to the power n. Therefore x plus 1 to the power n, x minus 1 to the power n, or we can write x minus 1 to the power n, x plus 1 to the power n. Now we have to differentiate both sides. n times, then what we have, that is we have y is equal to this much. Therefore, differentiating both sides n times by using Leibniz's theorem, we get that is dny dxn is equal to, that is x minus 1 n, nth order differentiation of that one, that is dn dxn of x plus 1 n plus nc1, that is n x minus 1 to the power n minus 1, that is the first, that is the differentiation, this term. Again that will be d n minus 1 dx n minus 1 x plus 1 to the power n plus dot dot dot. For n minus 1th term will be n c n minus 1, it will be n whole into x plus 1 to the power n minus 1 into d n minus 1 dx n minus 1 x minus 1 to the power n plus n c n x plus 1 to the power n dn dxn x minus 1 to the power n. This is the differentiation of this term, y is equal to this much, by using Leibniz's theorem. Now we have to put 1. Now putting x is equal to 1 on both sides of above equation, all the terms in RHS, that of right hand side, due to the factor x minus 1, here x minus 1, x minus 1, the term will be 0, except only the last term exists, since the nth order differentiation of x minus 1 to the power n is the n factorial. RHS, due to the factor x minus 1 except the last term vanish, and keeping in mind that the differentiation of this term, that is dn dxn of x minus 1 to the power n is equal to n factorial, we get, that is dny dxn, that term at x is equal to 1, at x is equal to 1 will be how much, that is all these terms are 0, only that term exists, that is ncn is equal to 1, x minus x plus 1 to the power n, that is 1 plus 1 to the power n, that is 2 to the power 1 into n factorial, that is 2 to the power n into n factorial. Now substituting x is equal to 1, substituting x is equal to 1 in equation, let I prefer, here is the equation number 6 and that one be the equation number 7. Substituting x is equal to 1 in that of equation 6, we get that is Pn of 1 is equal to C phi of x at 1, that will be Pn of 1 C phi of x at x is equal to 1, or Pn of 1 is equal to, that is C phi of x at 1 phi of x, that is dny dxn at x is equal to 1. The value will be this much, that is C into 2 to the power n into n factorial. Here we using equation number 7. Pn 1, or Pn of 1 is equal to 1, that is 1 is equal to C 2 to the power n into n factorial, that is Pn of 1 is equal to 1, or C is equal to 1 divided by 2 to the power n into n factorial. Now we get the value of C. We have to substitute the value of C in equation number 6. Then what we have? Substituting the value of C in equation 6, we get Pn of x is equal to 1 by 2 to the power n n factorial phi of x, that is 1 by 2 to the power n n factorial phi of x, that is dny dxn. Again the value of y 1 by 2 to the power n n factorial dn dxn, the value of y, that is x square minus 1 to the power n, that is Pn of x, that is Pn of x. Here we prove that one. This is the RODRIGUE'S formula. This is the required RODRIGUE formula for that of Legendre polynomial. So we see here the RODRIGUE'S formula for that of Legendre polynomial. We prove proceeding like this, taking y is equal to this much and differentiating, multiplying that factor n plus 1 times differentiation by using Leibniz's theorem, and substituting that quantity and proceeding like this. and finally prove that of RODRIGUE'S formula for that of Legendre polynomial. Now by using this RODRIGUE formula we can evaluate the Legendre polynomials. Take a look here. Legendre polynomial. Legendre polynomials. How we have? We know the RODRIGUE'S formula will be Pn of x is equal to 1 by 2 to the power n into n factorial d n dxn of x square minus 1 to the power n. Substituting n is equal to 0, 1, 2, 3 like that, substituting n is equal to 0, 1, 2, 3 dot we have that is p 0x that is 1 by 2 to the power 0 factorial that is equal to 1. Since we know 0 factorial is equal to 1. Again p1x will be 1 by 2 to the power 1 into 1 factorial d by dx of x square minus 1 is equal to 1 by 2 into 1 factorial 2x, 2 to cancel out, that value will be x. Then p2x will be 1 by 2 square into 2 factorial d2 by dx2 of x square minus 1 whole square is equal to 1 by 8 into d by dx of 2 whole into x square minus 1 into 2x. Again that will be 2 to 4 cancel out, that is 1 by 2 d by dx of x whole into x square minus 1 that is half d by dx of that is x cube minus x, that will be half 3x square minus 1 at the value of p2x, the value of p2x. Then p3x will be 1 by 2 cube into 3 factorial d cube dx cube of x square minus 1 whole cube, that value will be 5x cube minus 3x divided by 2. Here I take it as equation 1, equation 2, equation 3 and equation 4, that is p0 x, p1x, p2x, p3x. Proceeding as above, or also we have p4x. p4x will be 1 by 8 35 x fourth minus 30 x square plus 3, that is equation 5. here we write proceeding above, we may found values of P4x, P5x is equal to 1 by 8, that is 63 x to the power 5, 70 x cube plus 15x. Equation number 6. And P6 of x will be 1 by 16 2 3 1 x to the power 6 3 1 5 x to the power 4 plus 105 x square minus 5, that equation number 7. We proceed like this. Finally, we take the general formula for this, that is Pn of x will be summation over r from 0 to n minus 1 to the power r 2n minus 2r factorial divided by 2 to the power n to r factorial n minus r factorial n minus 2r factorial to x to the power n minus 2r. This is the general solution, general formula to derive all types of Legendre polynomials. Here, where n is equal to small n by 2 for even n, and n will be n minus 1 by 2 for odd n. So, we can easily express that of Legendre polynomials like P naught x, P1x, P2x, P3x like this by using the graphical representation of that of Legendre polynomials. Take a look here how I graphically represent the Legendre polynomials of P naught x, P1x, P2x, P3x and P4x are plotted between the interval -1 to +1. Let I prefer here graphical representation. This is, let here and here, this is +1, this is -1, upper half this is +1, that is, let that is -1, and here 0.5, here 0.5, how to draw the graph of that of Legendre polynomials. Look here, for that of P naught x, that is 1, that is P naught x. Here is the Pn of x, this is P naught x. Then for P1x is equal to x, that is the straight line from that of, I set that of range here from that of 1, here it will be a straight line, that is x. that is P1 of x, that is P1 of x is that line. Then P2x, that is have 3x square minus 1, P2x that looks like a parabola. P2x graph will proceed this way, the point this is the graph of P2x. Then P3x continued like here. This is the graph of P3x. This is P3x. Then P4x, the toss that of 5. This line is the P4x. This is P4x. This is a graphical representation of these Legendre polynomials like P0, P1, P2, P3, P4 versus that of x. This is x axis in the between the range -1 to +1. This is Legendre polynomials by using RODRIGUE'S formula, and we finally get the general formula. This is the graphical representation. So, with the help of this video lecture, we understand what is that of RODRIGUE'S formula for Legendre polynomials. We prove that of RODRIGUE'S formula by taking Leibniz's theorem and proceeding in this way, and finally prove that formula. And Legendre polynomials, by using that RODRIGUE'S formula, we can get P0x, P1x, P2x, P3x, P4x, P5x and P6x. These are the Legendre polynomials, and generalized these equations, and we have Pn of x will be this much, and a graphical representation of Legendre polynomials. This is just 4 Legendre polynomials in that of range -1 to +1. So, with this useful and informative notes, let me wind up this session. Thank you.